Alright gentlemen, I want to make it a quick video today. I know I said that yesterday and then I ended up doing an hour and a half's worth, but this one really will be quite quick. Just, oh, by the way, it's Juno here. Just doing some further investigatory work. I didn't plan on doing anything else, but I found some interesting evidence I wanted to present. So, very quickly, if you wouldn't mind, types of neuroinflammation will just be listed as below, and then we will do a brief explanation. So, face of injury, infection, or exposure to the brain, aging neurodegenerative disease, microglia upregulate inflammatory signals, resulting in neuroinflammation. Can be work as intended or can be harmful. Triggering of acute inflammatory response can become chronic and injurious. Neuroinflammation arises in slightly different ways depending on cause. All right, so in injuries, for example, concussive force or traumatic brain injury. So a knock to the head or enough impact can lead to a TBI, resulting in initiation of degenerative reparative mechanisms. These triggering of pathways alerts the immune cells and cause on it to generate an inflammatory response. Therefore, as a result of head trauma, immune system begins to send up pro-inflammatory cytokines. Cytokines are kind of like hormones for the immune system. They're signatory signaling molecules, such as interleukin-1 beta, which can worsen the damage caused by impact, leading to cell death, DNA fragmentation. Just so you know, so the signaling molecules themselves, they're not exactly inert, and in certain situations you can have a immune response that causes what is known as a cytokine storm. So all the interleukins are cytokines, by the way. Just use them interchangeably. I believe it was the old name was interleukin, and then they changed it to cytokine. But a lot of the molecules already had their names. I think there's a lot of them basically. Yeah, if you get you can have a feedback mechanism that sometimes occurs in an immunoresponse, and then that can be the genesis of autoimmune disorders in some given contexts. Nevertheless, let's continue. The additional release of tumor necrotic factor alpha along with the pro-inflammatory cytokines can sometimes lead to a compromise of the blood-brain barrier, reducing its ability to function as a gateway to the brain, protecting it from toxins. Just briefly, blood-brain barrier is constructed of like astrocytes and stuff, and the astrocytes basically just regulate what's coming into the cerebrospinal fluid. Spinal cord injury is slightly different. It occurs in 3 distinct steps. The first step sees compression or transection. Transection is just a cut of the spinal cord, trigger factors, or tear by the way, factors such as sodium and calcium ion imbalances, excitotoxicity of glutamates, or damage of the free radicals. This is interesting for me. Calcium and sodium ion imbalances. I'm quite interested to see the research surrounding the long-term implications of repeated exposure to those imbalances. Anyway, initiation of apoptosis, which is programmed cell death, following injury, along with the demyelination of neuronal cells in this inflammation at the location of the injury. All right, so demyelination, myelin is the grease, the lipid that covers the neurons that assists with depolarization of the neurons, electric transmission. And the cells that are accommodating for this in the peripheral nervous system are the Schwann cells. They just attach to the neuron, basically, the axon, and just keep it greased. They do like some stuff to do with metabolism as well. In the brain, though, these are done by oligodendrites. So it's like a Schwann cell, but it can do it to a bunch of cells at once. It's got a lot of hands. This triggers the second phase, which activates the reactive gliosis, edema, cavitation of spinal parenchyma, and can lead to an irrecoverable loss of spinal cord function. That's all pretty self-explanatory. An inflammatory response triggered by a spinal cord injury is linked with the secretion of pro-inflammatory cytokines such as interleukin-1 beta, interferon gamma, which is what I want to discuss today, tumor necrotic factor alpha, inducible nitric oxide synthase, and interleukin-6 and 23. The recreation of these cytokines triggers the activation of local microglia. Again, I would like to have a lot more information about that, please. And draws in bone marrow-derived macrophages, resulting in pathogenesis related to spinal cord injury. So, just before we get any further, there is a lot of research going on about exactly what happens in these neuroinflammatory events in terms of the blood-brain barrier. You know, what gains access to the CNS, and what effect can it have? And in the long term, if with the repeat exposure, all right, is there a residual emergent property of that? All right, let's continue. Peripheral immune system. Blood-brain barrier evolved to protect the brain from toxins that may enter the bloodstream. Endothelial cells and astrocytes, sorry. And forms a physical barrier between the bloodstream and the brain. Junctions of astrocytes regulate what passes through the barrier, but following an injury, this can be damaged, leading to an influx of T cells, B cells, macrophages into the brain, having impact of worsening inflammation. Okay, this is interesting here. Infections. Certain infections caused by viruses, bacteria, fungi, and even protozoa or parasites can cause encephalitis, inflammation. Meningitis, inflammation of the meninges, which is the cover of the brain and the spine. Each cause the infection activates a slightly different pathway leading to neuroinflammation. I'd like to see, again, more information there. In aging, cognitive degradation is often related to aging, but also neurodegenerative diseases have a higher prevalence in the older population, both of which are related to brain inflammation. Now, I know in Alzheimer's there are the accumulation of amyloid plaques and those neuronal fibrille things. I can't remember the word, I apologise. But this is actually seen as not secondary but complementary to, I think, other tau protein degradation. I'd have to look into that again. But anyway, let's continue. Research has shown that a healthy but aging brain has chronically increased levels of pro-inflammatory cytokines and reduced levels of anti-inflammatory cytokines. Again, interesting why. I'd like to see why that's the case and if that could be altered in any way. Demonstrating that the factor of age alone is linked with chronic neuroinflammation. Further research has uncovered that aging brains also have an increased number of activated microglia, a sign of activated immune system response, demonstrating another link between the aging brain and neuroinflammation. I'd also like to see whether or not we could identify neuroinflammatory events in younger people, right? In populations we wouldn't expect to see PD or Alzheimer's or anything like that, and see what the outcomes are like for them. Okay, neurodegenerative diseases. Neuroinflammation intrinsically linked. Alzheimer's disease, Parkinson's disease, multiple sclerosis, all related to neuroinflammation. To begin with, neuroinflammation is considered a major cause of degradation that is characteristic of AD. It is believed that those with the disease have an abundance of activated microglia that cannot phagocytize amyloid beta, which may lead or contribute to plaque accumulation. Neuroinflammation is seen as a major component of PD. It is believed to be inflammatory response in the gut. This is very interesting, I find. May be linked with the initiation of the disease, leading to inflammation of the brain, particularly of the substantia nigra, and disrupting the production of dopamine, which is characteristic of the disease. See, I would like to understand better brain-gut, GI-brain interactions. All right, is it all hormone neurotransmitter? Is there some gut biome interference there? Is something happening? Yeah, again, I'd like to know a lot more about that. Lastly, neuroinflammation is considered to play a major role in the initiation and progression of MS, multiple sclerosis. Research has shown the blood-brain barrier becomes disrupted in the presence of inflammatory cytokines, which allows for B cells and plasma cells to enter the central nervous system with a damaged myelin sheath that covers the neurons. Okay, it damages the myelin sheath. Does it damage oligodendrites or Schwann? Okay, because would there be a tolerance for this? Would there be some tolerance that could be accounted for? And if not, is there, as I speculate in other videos, is there some kind of not acidic, like a toxic environment? Is somehow a toxic environment established that prevents activity or even disrupts microglial activity? What covers the neurons? This demyelination is a major symptom of the disease, psychiatric disease. Finally, there's a large body of evidence elucidating the major role of neuroinflammation in various psychiatric illnesses. An emerging theory is stress plays a key role in initiating deregulation of the immune system in psychiatric diseases. We do already know, actually, that depression, stress, anxiety can have effects on people's immune responses in their body. So it is speculated that you will be you will have a lower activity of your immune system if you are chronically stressed. And that can be compensated for in the body, but what about the brain? All right, and environmental factors. This immune system activation has been seen to cause abnormal neurotransmission, resulting in serotonin deficiency and the increased production of neurotoxic substances, decreased progression. Schizophrenia, autism, depression, and other mood disorders have been linked with inflammation of the brain. However, the exact and the mechanisms of relationship are specific to each illness. All right, I will be back in just 2 seconds. Interferon gamma potentiates GABA alpha receptor mediated inhibitory currents in the hippocampal CA1 pyramidal neurons. All right, so I want to look at this study very briefly. Again, I'm trying to keep this short today. Basically, they want to investigate interferon gamma in its role as a neuroinflammatory molecule, cytokine, Its interactions with GABA, and they use they basically use slices of hippocampal matter, and then they're able to what does it say here? Spontaneous miniature postsynaptic inhibitory currents and tonic currents in hippocampal pyramidal neurons by the whole cell patch clump method. All right, so they're able to investigate it by changing levels, making amendments, and then passing the currents through and detecting the outcomes. Okay, in conclusion, the potentiation for GABAergic currents in hippocampal neurons by interferon gamma may contribute to the disturbed neuronal excitability and cognitive dysfunction during neuroinflammation. All right, so we are seeing a relationship, at least in a complementary fashion, between interferon gamma and GABA. And this I find very interesting. Why? Because I want to see what role interferon gamma plays in the greater context of neuroinflammation, specifically with the gearing towards what contributions that may make in long-term exposure to neurodegenerative conditions. So, interferon gamma directly induces neurotoxicity through a neuron-specific calcium-permeable complex of interferon gamma receptor and AMPA glury receptor. I'm not going to spend too long on this again, but the abstract's very clear here. Interferon gamma is a pro-inflammatory cytokine that plays a pivotal role in pathology diseases of the central nervous system, such as multiple sclerosis. All right, so we already have that established. However, the direct effect of interferon gamma on neuronal cells has yet to be elucidated. We show here why interferon gamma directly induces neuronal dysfunction, which appears as dendritic bead formation in mouse cortical neurons and enhances glutamate neurotoxicity mediated via alpha amino 3 hydroxy 5 methyl 4 isox azole propionic receptors, but not N-methyl D-aspartate receptors. In the CNS, interferon gamma receptors form a unique neuron-specific calcium-permeable receptor complex with AMPA receptor subunit glury. Through this receptor complex, interferon gamma phosphorylates glury serine 845 position by JAK2 STAT1 pathway, increases calcium influx and following nitric oxide production, and subsequently decreases ATP production, leading to the dendritic bead formation. These findings provide novel mechanisms for neuronal excitotoxicity, which may occur in both inflammatory and neurodegenerative diseases in the CNS. Excellent. Very interesting. Let's move on. GABAergic glutamatergic imbalance relative to excessive neuroinflammation in autism spectrum disorders. Interesting. All right, now we're starting to get into the thick of what I want to discuss. So, we've already looked at interferon gamma. We've looked at the role in neuroinflammation. We've looked at interferon gamma interactions with GABA specifically. Now, we already understand from our previous videos, some of the interactions between glutamate and GABA, and the relative balance that you will find with them in the synapse in neurons. So very quickly, I'm just going to look at, I think you can extrapolate what that is here, but let's look at it. Conclusion: multiple regression analysis revealed associations between reduced GABA level, neuroinflammation, and glutamate excitotoxicity. This study indicates that autism is a developmental synaptic disorder showing an imbalance of GABAergic and glutamatergic synapses as a consequence of neuroinflammation. Now, I think this is fascinating. I think this is very interesting. The problem is, okay, how do we intervene to rectify such an imbalance then? Is it merely going to be enough to upregulate GABA itself? Or do we need to look more closely at the synapses and see if there's anything we can alter in them to balance out GABAergic and glutamatergic synapses? And if that is the case, what role does that then play for autism in relation to neurodegenerative conditions? We already know that many neurodegenerative conditions present dominantly in males, at least in younger ages. Could there be an implication, therefore, that autism could be an early presentation of the same pathology that will then lead later on to neurodegenerative conditions in later life? Tramiprosate in mild to moderate Alzheimer's disease, a randomized double-blind placebo-controlled trial multi-center study. All right. Again, I'm not going to read the whole abstract, but please just do that in your own time if you want. The primary plan analysis did not show a significant treatment effect, but they were confounded by unexplained variants. Post-hoc analysis showed a significant treatment-related reduction in HV loss. However, there was only a trend towards slowing of decline of ADAS-Cog and no slowing of decline in the CDR-SB. These results must be interpreted in consideration of the limitations of the clinical disease modification outcome measures and their relationship, the heterogeneity of the disease, and the impact of confounding demographic clinical variables. I did want to include this. I know it's not entirely in congruence with my hypothesis that I'm presenting today. Nevertheless, I thought it was interesting that it be at least included, so letting you know I am aware of the work. Now, moving forward on this relationship that I made between autism potentially and neurodegenerative conditions in the long term, I want to focus here on GABA and multiple sclerosis. So in this study, we're looking at homotaurine, a safe blood-brain barrier permeable GABA AR-specific agonist, ameliorates disease in mouse models of multiple sclerosis. Now this is very interesting for me, and I will read the abstract in this case. There is a need for treatments that can safely promote regulate lymphocyte responses. T cells express GABA receptors, and GABA administration can inhibit the Th1-mediated process such as type 1 diabetes and rheumatoid arthritis in mouse models. Whether GABA agonists can also inhibit the Th17-driven processes such as experimental autoimmune encephalomyelitis. A model of multiple sclerosis is an open question. GABA does not pass through the blood-brain barrier, making it ill-suited to inhibit the spreading of autoreactivity within the CNS. Homotaurine is a blood-brain barrier permeable amino acid that antagonizes amyloid fibril formation and was found to be safe but ineffective in long-term Alzheimer's disease clinical trials. Okay, so maybe it could be preventative then. Homotaurine also acts as a GABA AR agonist with better pharmacokinetics, than that of GABA. Working with both monophasic and relapsing remitting mouse models of EAE, we show that oral administration of homotaurine can 1. Enhance CD8, CD122, PD1, and CD4 FOXP3 TREG, but not BREG responses. 2. Inhibit autoreactive Th17 and Th1 responses. And 3. Effectively ameliorate ongoing disease. These observations demonstrate the potential of blood-brain barrier permeable GABA AR agonists as a new class of treatment to enhance CD8 and CD4 TREG responses and limit Th17 and Th1 mediated inflammation of the CNS. Here we go. Mediated inflammation of the CNS. Homotaurine. What are we looking at? Multiple sclerosis, Alzheimer's, PD, ALS, MND. Okay, interesting. Was there anything additional in the conclusion that I wanted to make sure was included? No, I'll just leave it at that then. Okay, so moving on. Medical research, yes, it's Sisyphean endeavour, fair enough. Where did I want it exactly? Alright, brain chemistry labs, non-neuroscientist, but ethnobotanist. Someone who studies the relationship between plants and human society, helping develop the theory that BMAA and cyanobacterial toxin could in part cause neurodegenerative disease. Okay, fair enough. In part, it could be an element of it. Research followed several indigenous groups in the Pacific Islands, again, the Guam people. But one of the groups he studies, the Ojimi, an indigenous tribe in Japan, had low incidence rates of neurodegenerative disease. The diet of the tribe consisted of foods high in L-serine like seaweed. Now, wait for it, okay? Homotaurine. Again, homotaurine, also known as tramiprosate, is a natural amino acid found in seaweed. It is analogous to taurine, but with an extra carbon on its chain. It has GABAergic activity, apparently by mimicking GABA, which it resembles. It was investigated in phase 3 potential, but it didn't show efficacy. A study of cognitive impairment done showed it did have positive benefits. All right. Now, does this mean, therefore, potentially, that while homotaurine may not exactly be ameliorative to AD or PD or any other neurological conditions, could it offer a preventative measure? And if so, how is it preventing neurodegenerative pathology from developing? I think that is well worth an increased study. Again, I said it'd be a short one today. It's a very quick A to B from neuroinflammation, autism, interferon gamma, GABA interferon gamma, glutamate, excitotoxicity, then on to homotaurine, and the again just briefly rehashing the seaweed stuff, and then trying to relate it all back on itself. All right. Well, I hope you found that investigation interesting. I'll admit I didn't come to any very broad conclusions. However, I hope I've been able to elucidate some of the material and draw out some additional observations that could be drawn. And I will be adding this to the playlist if anyone else wants to view it. And I hope it will be productive in the long term and contribute to something. I'd like to thank all of the various publications that make their information available for free. That's of great use for all the people who take an interest or are fascinated by this field. And I think for now this will be all I release on neurodegenerative conditions and neurology generally. I think I've explored a lot of what's already available. I think I've made it clear where my understanding is limited and where I can look to improve that understanding. And I don't think at the moment I'm going to be seeing, from what I've seen at the moment, anything additional that would be worth discussing, that I would be prompted or feel compelled to discuss. That being said, I understand there's a great deal of research and funding going into neurology from a COVID perspective, and following up some of that work, I may be cross-referencing videos in future, just a couple, I hope, that won't be added to necessarily this playlist, but may have its own mini playlist on my YouTube channel. And again, that will be specifically looking at the neurological effects of the COVID-19 epidemic and the ongoing struggle to understand exactly the implications and mechanisms by which people are suffering from apparently neurological conditions after infection. All right, well, again, thank you very much for joining me. I hope you found that interesting, and look after yourselves.